I hope this example will be clear to everyone. Still, if you have any confusion here, just let me know during the QA session and I will explain this again. So once we have these values calculated, what is the next step? So consider a neural network here, which is a little bit more complex as compared to previous one. And in this neural network, we have two hidden layer here. So this one is the input layer with 4 input neurons, and we have this output layer here with 2 output neurons, and we have these 2 hidden layers, each hidden layer containing 4 neurons. So in total, we have 1 input layer, 1 output layer, and 2 hidden layer hairs. Now, uh, just calculate the same procedure or same steps which we did earlier to compute the weighted sum and the activation function here. So when we pass the input data here and we have a forward pass here, we will be calculating all these values, and we have the output of the network here as the output value. And also we have a target value here. So now what we will be doing is, in backpropagation learning, we will calculate the difference between the values computed by the network and the actual or desired output. So we will be having a difference or a error term here, which is the difference to the desired values. Now, mathematically, it can be explained as E out, which is the error at the output layer, and it is the difference between the desired output. Here, D is for the desired, out is for the output layer. So, at the output layer, we have error, and this error is the difference between the desired output value and the actual output value of the input. So once we compute the summation of all the error values here at the output layer, and their squared sum will give us the total error generated at the output layer. And then as I explained earlier, we need to backpropagate this error on to the hidden layer. So backpropagation from the output layer can be computed as the error at the output and all the weight vectors at the output layer. So we are doing a weighted sum of the weight vectors present at the output layer and the output error term which is computed here, and their weighted sum will give us basically the error of the hidden layers, and then we can calculate the difference of the hidden layers by using the same thing. So you saw that how we are using the values computed by the network and the desired output values, and then we are basically computing the difference which is giving us the error term, and then we are calculating the total error term, and then we are basically back propagating it from output layers to all the hidden layers, right? So this is the step 3 of this backpropagation algorithm. Now how this error is being transported. So again, look at this network which we discussed earlier, and you can see that it is a fully connected network in which each neuron is connected to its proceeding neurons in a fully connected manner. Now here this green circle shows the difference to the desired values, right? So we have this difference which is the difference between the desired value and the actual value, and we are basically back propagating this difference from output layer to this hidden layer. So initially this difference will be back propagated from output layer to the hidden layer, which is at the back of the output layer. Then when we have the errors calculated at the hidden layers, then the next thing will be to transport this layer from this hidden layer number 2 to hidden layer number 1. So you can see here that once we have calculated the error at the hidden layers, which is being shown here with these green circles, and we are basically transporting back these errors on from hidden layer 2 to hidden layer 1. And in the same way, if we have another hidden layer here, then these errors will be computed from this hidden layer, and then these errors will be transported back to the previous hidden layer. So this procedure will be followed for each layer and for each neuron in each layer, right? Okay. So let's do a bit summarization which we of the discussion which we had. So in multi-layer perceptron, we perform training by using the backpropagation algorithm, and in backpropagation algorithm, we compute a cumulative error, which is denoted by E because it's for error. So we compute a cumulative error over a data set for we are saying data set here because we compute these errors for all the training examples in the whole data set, right? So you need to do this thing for the all the training samples in the data set, and it can be written as a function of the network weights, right? So you will see this mathematical expression is basically the summation of the desired output value and the difference of the desired output values and the actual output value, and we are computing a squared sum here, and this thing will be performed for all the training samples present in the data set, right? And then we will have this error, the final error. Let me explain it again. We are computing the difference between the desired value and the actual output value, and we are having a squared sum of this error, and we are calculating this error for all the training samples or all the training examples present in the database, and then we will have our final error. Here dj is the desired output value of node j, right? So here this subscript j is basically specifying a single node here. So for node j, dj is the desired output value and oj is the actual output value. The error is squared so that the positive and negative errors may not cancel each other during summation. So why we are doing this square here is that because we can have some positive values or maybe some negative values when we are having this difference. So if we have some positive and negatives, the chance is that they may cancel out each other. So in order to avoid that, we are basically doing square here so that all negative values can be converted to the positive values. Okay, let's have a look at what does it mean about the local minima or global minima and how these local or global minimas can affect our training. So each weight configuration can be represented by a point on an error surface. Let's suppose that we have this error surface here, right? Where we have this weight vector and the error, and on this error surface we have our weight vectors, and we are basically trying to adjust those weight vectors accordingly so that we can have the correct classification. So on this error term, we are basically trying to minimize the error, or we want to go down on this error surface so that the error could be reduced, or the loss function could be reduced, and we can have correct classification. So initially, when we initialize our weights randomly, we have w1 here. So let's say that this weight vector is the old weight vector which we have initialized randomly, and then when we do this backpropagation rule and computation of error and adjustments of weight, and then when we calculate the new weights through delta rule, we let's say we have the new weight here as w1 new, which is a new weight. So we can see that the new weight vector is going down on this error surface, and this weight vector is much better as compared to the previous old vector, right? So we basically want to go down on to the error surface so that we can minimize the error after each iteration of the weight vector. So when we reach here, then this is basically the local minima of this error surface, right? And we have this global minima here of the error surface here. So sometimes it happens that we got stuck at the local minima, and we won't be able to go towards the global minima. But there are some other ways which I will say that out of the scope of this lecture. So basically we want to go down with each iteration, and we want to have new weights on this error surface, and we want to achieve local minima or maybe a global minima. So right, this was I will say more or less the overall explanation of the neural network. Let's do a summary of all the things which we discussed so far.